Okay, let me restart this lecture with an example of what we have seen so far. Maybe it's worth if we stop for a moment looking into the theory. Now we try to put this at work so that you have a better understanding of what we have seen so far, and then we will have time to go in more detail doing practical experiments on this theory. So let's imagine that we want to model something on using Simulink. Then we want to generate this model into a code, and then we want to deploy the code on the evaluation board that we have available. We will analyze the full executable export, okay? And then we will analyze also the algorithm export. So let's imagine that we have a very simple model that is this one. Our task is to take control of one of the resources available on the board. In particular, we want to generate a square waveform on that output, because our application requires to have a certain waveform on the output. So we can use Simulink. Have you already used Simulink in the past? Yes, okay, so you are used to the approach of Simulink. You have the libraries in the library browser. You can drag and drop symbols from the library browser into the schematic, and then you do the customization of the component that you just dropped. So among the sources, let's take, for example, the square wave. So I think there should be somewhere, so a pulse generator. We drop here. Okay. Then we want to give a certain configuration of this, let's say amplitude 1, period, let's say 1 second, pulse width 50% of the period. So we have a square wave with a duty cycle of the 50% and period of 1 second. So this is the configuration of our design. So here we generate the pulse, then we can also have a look at the pulse just to be sure that it is doing what we are expecting. Then we can open this and we do the simulation. So nothing very relevant. We just have the square waveform that we are expecting, okay? Now, let's say that we want to take this model. This is our controller. We want to deploy this on the board. And we want to visualize the output of the pulse using one digital I/O. For example, we want to use the blue LED. What's the scenario here? Let's imagine that this output is the output that you have to provide on a certain actuator whose operation is modulated through this pulse that is basically a PWM. So here we have a pulse width modulation that we can generate on the board to take control of one actuator, okay? For the moment, instead of mapping this output on any of the IOs that are available on the connectors of the board, I just want to drive one LED so that I have a visual feedback of what is happening. So thanks to the fact that we have a platform super package, so we have the capability of doing a full executable export, we look into the Simulink library browser for the embedded code support package for the Freedom board. We take, for example, the digital write, we drag it on the schematic, and then by double tapping here, we can do the customization of the component, and we select the blue LED as the pin to which we want to deploy our hardware, our controller, okay? So now we can ask embedded coder to translate the model into code, then to compile the code, create the executable for this target, and then to program the board with the new executable. This is done using this button here, deploy to hardware. So what we are doing here is a very simple full executable export. We click here, then this takes some time. If you look at the diagnostic viewer, you will see that there are some messages that are appearing on the screen. First, we have the code generation. So the model is translated into C code. Then we have the generation of the software platform, that is the scheduler, the driver. Everything is linked together, and the board is programmed, and you can see that now we have a blinking blue LED with the selected frequency. Very simple example, but here you have seen at work all that we have seen this morning. So you have modeling with platform independent language. Here we haven't said how we can write to the resource, selecting the proper GPIO, selecting the proper color, and so on and so forth. We just instantiated the block that generates the pulse we need to have. Then we instantiated a block. We don't know nothing of what is behind that block. We just say that that is the block that will correspond to a physical resource. For us, this digital variety is an abstraction. It's an abstraction of a physical resource. We don't care about how this resource is implemented. Then we have done the simulation. We are happy with the simulation. Eventually, we deployed everything on hardware through full executable. And this is the hardware that is doing what we want to achieve. Then, if we want, we can have a look at the code. You can see here, this is the code generated in this process. We have a main function. We have a number of source files corresponding to the model that we have created, plus some utility file and interface files and other files corresponding to the software platform that we are using. You can see here we have a middleware custom RTOS header. This is the service of the software platform providing the operating system. Target hardware resource, well, this is the header file that contains the definition of the input-output resources that are available on the board. All of this is automatically generated. If we look into the main code, we see that it is a piece of C code with a main function that does some operation and then create a task middleware RTOS init. This is a task that is created with a period of half a second. This is exactly the property that we specified for our model. We want to have a pulse that has a 50% duty cycle with a period of 1 second. Then if we look inside this, I think we will have oh, why is not here is the Freedom 64F RGB LED step. This is the function corresponding to our model. We will see this more in detail later on. So this is the function that implements the behavior of the Simulink schematic. Basically, what we are doing here is to keep track of the time that is changing, and then if we reach to the semi-period, then we switch the output from 1 to 0 or vice versa. It is not relevant for the moment that you understand all the details of this. What is relevant is that you understand the concept. So we have the model, we generate the C-codel, we generate the platform, we assemble them together, and we deploy on the hardware. This is an example of full export. If we do algorithm export, we will see only the code that it is contained in this file. We will not generate the code for the driver. We will not generate the code for the operating system. We will generate the code only for the application. And so we have only the code for initializing the execution of the model, terminating the execution of the model, and then executing one step of the model. We will see this later on in greater detail. What is relevant again is the concept. If you do algorithm export, you see only the code that I am presenting now on the slides. If you do full executable, you will see this, plus all the accessory files containing the software platform along with the algorithm. It is clear that there cannot be difference for what concerns the algorithm if you do full executable export or just algorithm export. Obviously, the algorithm is contained in the full executable. So the two activities produces the same code as far as the algorithm is concerned. Then around the algorithm, in the case of full executable, there is more. There is the operating system, the drivers, and the two are fit together nicely. Okay? Is this clear? Then this is what you do when you deploy everything to hardware. Let me see if we are able to do something different. That is the processor in the loop simulation. No, external. So what I'm trying to do here is to have the simulation of the model here, but the visualization of the output on the on Simulink. So it is what we have seen before, the co-simulation of the controller on the hardware with the plant in Simulink. Let me see if it works. Okay, where is it, the output? You can see the waveform now. You see that the simulation is not immediate as before. You have seen that it takes some time to draw every single step of our schematic. This is because the software is running here, so the model is running on the hardware. Then every time one execution step of our controller is done here, there is a communication between the board and Simulink so that we can update the scope. Okay? So here you have an example of the co-simulation of the code running on the processor, on the external processor, with the plant that is running on Simulink. This is an example of processor in the loop simulation. Here it is called external because that is the specific configuration that is supported by this platform package. But the concept is the same that we have seen on that chart. We have the code that has been deployed on the real hardware. The real hardware is executing the controller. In this case, it is a very simple pulse generator. And then the output of the pulse generator from the board is provided to Simulink that is able to display this. And you have seen that the time Simulink takes to update the waveform is not negligible. This is because we have communication between the target and the computer. When we do normal simulation, it is immediate. You've seen that we just tap on run and the waveform appears. This is when we do model in the loop simulation. In this case, both the model of the controller and the plant are executed on the computer. Obviously, the time has nothing to spare with the time the embedded hardware takes for running our software, because everything is done on a totally different hardware. Okay? So you have seen that through this platform support package, we're able to support different elements of the design flow with this board. So that's why I'm asking you to buy this board, because you can put at work the things that we have seen in theory. Differently from what I announced in the slides, you should use the version 2016A of MATLAB, because this is the only version that supports this platform support package. It is very simple to do what we have seen with this platform support package. So it is better if you use that. It will make your life easier. Any question, doubt? Okay. So what I suggest you is to install 2016A so that starting from next lecture, we can do some advancement on the modeling of controllers. What I want to address is how to model using Stateflow. You already have seen Simulink, so you already have been exposed to that way of simulation. Something that you haven't seen yet is how to model controllers that are finished state machine. So we'll do this together. And for this, it is much better if you have the laptop with you and Simulink and Stateflow installed so that we can do an interactive lectures. Okay? So please, for the next week, have MATLAB 2016A on your machine. Bring the laptop in class So we do some model in the loop activity together. The board is not needed yet, okay? But the laptop and Simulink, yes. Okay? Okay. If we aren't done yet, we still have half an hour, okay? So don't put things away. This half an hour was just to decompress a little bit, then we resume with the lectures. If you don't have this exact version already installed, as long as we don't need to use the board, it's not an issue. So you can use whatever you have, because the tool is always the same. But when we receive the board, you should upgrade to 16A. Okay, so after this little exercise, let me go back to the slides. Because I want to talk about modeling languages. We have plenty of modeling languages that are designed for specific applications. We have seen we need to do a controller with finite state machine behavior. We do state flow. We have to do a traditional PID controller while we do Simulink. Depending on what you want to express on your model, you have different domain-specific languages. I try to define a classification of this that we can try to explain using this abstraction domain space. So on one axis, you have the abstraction, so the amount of detail you want to put on your model. The other axis is the domain, that is the feature that are relevant for the model that you are building. This is coming from the digital design theory, where you can find these abstraction levels and these representation domains. Let me say that the abstraction level is the degree of details, so how much detailed your model shall be. It can be so detailed that you describe every single physical device that is part of your model, or it can be very abstract. You just have a representation of the functionality that the system exposes. Then the representation domain deals with the aspects that are of interest. Do you want to convey just the behavior of your model, or do you want to represent the physical geometries of each piece of silicon that is in your system? So the higher is the abstraction level, let me say the bigger is the lens that you are using to look into your system. If you are at the device level, you have a very tiny microscope to look every single bit of your model. If you are at the system level, well, you have a kind of sunglasses to have a very high-level view of your system. If you work on the representation domain, you look at the characteristics of the model you want to represent. Do you want to represent the behavior? Do you want to represent the structure? You want to represent the physics of your model? You want to represent the geometry of your model? These are all elements that you can consider. Putting together abstraction level and representation domain, you have different squares corresponding to different types of model that you can build. Let me move here. Here we have an example of a behavioral system level description. Here we are interested in what the system is doing in very abstract terms. For example, we are willing to model the behavior of a system that could have two operational states. There are transitions between states that happens according to a certain logic, and then there are actions that are taken when entering each state. As an example, we have the off state and the on state. These are two ways for representing two conditions in which our system can be. Then, in the off state, we say that a certain object that is called LED shall be set to 0, while in the on state there is another object that is called, the same object that is called LED shall be set to 1. Then the transitions between the two happens after 1 second we entered in the state. So if we are in off state, after a second we go in on state, and then after 1 second we entered in on state, we go back to off state, and so on and so forth. So this is very abstract. What does it mean that we have a state? What is a state? It's just a condition in the execution of our system. Then what is a LED? Well, it's an object. What's the meaning of 0 and 1? Well, two values. There is no specific physical meaning here. We have just a behavior. Then, when we want to move to a more detailed modeling of this system, we may want to move from a higher abstraction layer to a lower abstraction level. So from system to RT. RT stands for register transfer. So here we have a model that conveys the same behavior, but it is more detailed. We have more information about how the behavior is implemented. In this case, we decided to code the model using the C language. What you see here is a fragment of the operations that embedded coder decided to use to write a C code that is functionally behaving exactly as the model that we have seen before. Here we have more detail. We have a temporal counter that is incremented until it doesn't come to 127. If it is, otherwise it remains the same. Then there are if statements to decide whether to switch the LED on or off. This is a set of statements that are resulting from the generation of the translation of this algorithm into a piece of code. It is evident that the higher is the abstraction level, the easier is to understand what is happening inside that model. I bet that if you start looking at this, you will not understand what is happening. While with this is immediate. It is clear. It is very high-level language that describes in a very simple manner which are the operational state and what is happening between these states with very high-level constructs. This is C program. I don't want to write this. This is something that I derive automatically from that. I want to model at this level where it is easy to reason about the behavior. Then this, it is what I need for implementing the behavior, is done automatically. Okay? Another technique for modeling is this one, where we want to convey the structure of our system rather than the behavior. Let's imagine that you want to design a filter. A filter can be implemented as a linear combination of delay plus sum and gains, like this one. This is a median filter that takes 3 samples and computes the average over 3 different instances of time. Okay? Well, you can implement this using a state machine. but maybe it's complex. It is complex because if you look into the books of filters, you have a lot of schematics like this one. So it could be very simple to reproduce the functionality through a structure. So you can put together elements out of the Simulink libraries, obtaining something like this. Then this is a system-level representation. You have complex operators. You have sum, gain, delay. These are complex operators that you can put together, you can simulate, and then you can translate into code by obtaining a C code that is a behavioral representation of the structure that we have just seen. This is done automatically through the transformation rules. And this is a representation of code generation. We do code generation when we move from a higher abstraction level, the system level, to a lower abstraction level, the RT level. Code generation can be done starting from behavioral description, state machine, state flow, or structure, Simulink schematic. Okay? Do you have question? Okay, so in this block of slides, we have AutoSAR. Okay? We will keep this on hold for a while. I want to spend next week working on modeling with Simulink. I want to spend next week to have a look at the code generation process more in detail. Okay? So, starting from next week, please have the laptop with Simulink installed so that we can do some experiments. Okay? Any question, comment? Okay, see you next week.